Thank you. Good morning, everybody. It is my great pleasure to be here, and I'm really thankful to the organizer for allowing me to speak here in this very interesting meeting, and essentially in part honoring these three gentlemen that basically made crucial contributions to the field of topological matter. Today's talk, is basically a talk about topological superfluidity. There is some overlap with yesterday's talk by Saro. Essentially, I'm interested in studying, many fermion interacting systems with repulsive interactions, and essentially trying to figure out what a topological superfluid is in a number conserving system. Okay, so I will explain what I mean exactly by that. And essentially, what I'm going to talk about today, it's not even published. So it's work that is really new development, very recent work that is a natural continuation of previous work that I've been doing in the last few years, where I've been trying to answer this question of what topological superfluidity is. How is that you distinguish topological superfluidity from standard or non-topological superfluidity, like, for example, in helium-4, okay? And essentially, given the fact that there is a lot of interest in, coming from Microsoft and from many companies trying to build a topological quantum computer, it is very clear that we need to understand very well what is the meaning and what is the fate of these Majorana quasi-particles or excitations in the context of number conserving systems, okay? So before I proceed, indeed, I would like to acknowledge my collaborators, in particular, the main driving force for this work that I will present today is Leonid Isaev. He's a postdoc at Gila. He was a former student of mine. And indeed, Anna Maria Reid, also from the same place. She is essentially the person that knows the best about cold atoms. That is essentially the platform that I will be describing. So let me start, So let me start, basically giving you my context, my motivation for this talk. Okay, so as you know, what we've seen so far, most of the work on topological quantum matter, topological superfluid is a particular case of this, but most of the work on topological matter is based on the mean field quasi-particle picture. Of course, there are exceptions in quantum Hall, but if you go to topological insulators, topological superconductors, topological superfluids, it's done in this mean field quasi-particle picture. So, sorry, it's an experiment. It's my first time doing the thing. And indeed, the reasons are very simple. First, if you're a mathematician, it's mathematically simple. From the mathematical point of view, this represents, semi-simple Lie algebras. And indeed, if you want to solve this problem, this has polynomial complexity as opposed to exponential complexity with a number of degrees of freedom. So it's a very simple thing. Now, if you're a physicist, of course, it's very intuitive, okay, after Landa's work on quasi-particles, because, it's a very nice picture, a single particle picture. And also, if you're a mathematical physics or some theory, indeed, it's very convenient because you can build all kinds of topological invariants, okay, for non-interacting systems, and they come in different flavors, Chern numbers, Berry phases, winding number, Bott index, Hopf index. It's a zoo of numbers that in some way or another essentially characterizes these phases, and in some cases, you can classify, okay, these phases. So, okay. But now, having said that, indeed, how is that experimentalist, okay, will establish that she or he, okay, has discovered a topological state of matter? Indeed, the principle that is usually invoked, okay, is this. Oh la la. I'm sorry. I don't know. don't know why it doesn't work. Okay, so the principle that is invoked is typically this bulk boundary correspondence. Okay, so there is some sort of correspondence between the topological vacuum and some symmetry-protected boundary of defect modes. Okay, and these come in different flavors. Indeed, for topological insulators, they are fermions, and in the case of topological superfluid, they are Majoranas. And that's the reason why there is a lot of interest in topological superfluids or topological superconductors, because indeed, through this kind of bulk boundary correspondence, it turns out that you can get some sort of excitations, okay, or modes that essentially have special properties, like, for example, non-abelian braiding, okay? Okay, but real materials are interacting systems, and, you know, in general, number conserving, okay? And this number conservation is an important concept, in particular in the context of superfluid or superconductors, okay? Of course, I mean, you can have open systems, in which case, you know, number conservation, it may not be an issue, okay, but in general, I mean, number conservation is an issue. I'm sorry, this is slow. So, and then there is a set of questions that emerges that, you know, for example, what does it mean to have a topological state of matter? For example, a topological superfluid in a many-body interacting system that has number conservation, okay? Do we have a bulk boundary correspondence? What is experimental signature? What is localized many-body mode? What is the meaning and fate of Majorana modes in interacting systems, okay? And how much of the mean field picture survives, okay? That's a very general question. Now, why do we care? As I mentioned before, now there are lots of companies that are interested in building computers, in particular topological quantum computers. And indeed, you know, there are many claims of observation of Majorana modes. But, you know, from my perspective, I mean, the real interest, I mean, in these Majorana modes is basically on the fact that you can perform non-abelian braiding. Okay, not the fact that you have a zero conductance, you know, a peak, or the fact that you see some bump at the end of a wire. Okay, that is useless. So the real use of the thing is because you can braid those things and you can perform certain gates. Okay, that is the real interest. So sorry. Okay, so basically this says more or less what I said before. And indeed, I mean, we have some answers to the questions I mentioned before. Okay, so for example, we have the answer of what is a particle conserving topological superfluid. So if you have a closed system, okay, where there is no exchange of particles, the number of particles conserved, we know how to characterize this topological superfluidity in terms of what we call fermion parity switches. Okay, so fermion parity switches is indeed a very simple concept. The concept is essentially you take, you know, your many-body system, your, you know, I don't know, whatever number of particles you have in your system. You can pick up the model you want. I mean, have our model, you know, in whatever the number of dimensions, whatever, and you have to compute essentially the ground state energy, okay, of basically, let me see if this works. Basically, you have to calculate the ground state energy, okay, for a certain, you know, boundary condition. It could be periodic or anti-periodic boundary conditions for n particles, okay, for n plus 1 particles, okay, and for n minus 1 particles. Okay, so you calculate essentially these 3 ground state energies for basically periodic and anti-periodic boundary conditions, and what you do is essentially you form what is called the fermion parity switch. The fermion parity switch is something like, you know, E0 phi n plus 1 is essentially the inverse compressibility, minus 1, minus 2 is 0, let's say, of n. Okay, and you see with this whether as a function of boundary conditions or fluxes, essentially there is a twist. I mean, if there is a crossing of this, there's a change of sign of this parity switch. So essentially what happens if you take any model as a function of fluxes, what happens is if you start at periodic boundary conditions, if you start with periodic boundary conditions, what happens is that you may start with the odd sector, okay, or with, this is E odd. Let's say E odd is the sum of this divided by 2. Okay, E odd, E even. E even, yeah, it's not very good. And then there is a crossing as a function of flux. Okay, so whenever you have something like that as a function of flux, what happens is that the system is topological. Okay, if you don't have this crossing as a function of flux, essentially the system is trivial. Okay, so the point is that indeed this allows you to characterize any system. Okay, so you can use this as basically sorry? You apply some flux. It's a change of boundary conditions, essentially. It's a change of boundary conditions, okay? So although we have answered this type of questions, indeed, I mean, the question we have not answered is what happens, in the case of Majorana many-body modes that you can construct from the system. Although we constructed some of them, indeed, there are some problems, okay? There are some problems. I am not going to talk about this. If you want to learn about these problems in these works, okay? And indeed, the big problem is that there could be some violation of charge superselection, okay? So the point is that if you are just dealing with the usual BCS type of physics, okay, by definition, which does not conserve the number of particles, by definition, if you have a zero mode, indeed, there is always a Majorana mode that is zero mode, by definition. I mean, this is just a structure of the Hamiltonian, of the BDC Hamiltonian, that essentially has, no matter what kind of interaction, no matter what you have, indeed, it has an anti-unitary operator that anti-commutes with the Hamiltonian, which means that the spectrum is symmetric, the single part of the spectrum. And if it's a zero mode, it's very easy to show. It's just 2 lines. This is a Majorana mode. So Majorana modes are part of the hardware, okay, of a mean field picture. Okay, it's not so obvious if you don't have a mean field picture that you will have this type of excitations. So indeed, let me skip this because otherwise I'm not going to talk about what I want to talk about. So what I want to talk about, indeed, is now try to essentially build these superfluids, number conserving, in the platform, essentially in the cold atom platform, okay, with fermionic atoms, okay, in optical superlattices. Now the idea is, of course, we can write down whatever Hamiltonian we want, but that's not the point. The point is to use all the physical interactions that experimentalists, okay, can realize in the lab, and essentially try to design, use some principle to design something that, despite the fact that you have repulsive interacting fermions, you still can have a superfluid, okay? And we do not want to use, for example, to produce a spin-orbit coupling, because there is heating. There are some problems with spin-orbit coupling. So we want to do some effective thing such that we have topological superfluidity. So I'm sorry, this is slow. And so let me skip the thing because this is basically also motivation. So let me tell you what I'm going to do now. What I'm going to tell you now is essentially how I can create fermion pairing and superfluidity from repulsion, okay? Then I will show you some sort of new mechanism, okay, to do that. Then I will show you that this mechanism can be realized not only in one-dimensional system, but in two-dimensional or three-dimensional optical lattices, okay? Indeed, because, as I said, my goal, the final goal, is trying to get something that is a topological superfluid, and where I have Majorana excitations, if they are there, okay, and these Majorana excitations can be manipulated, okay? That is the whole idea. So to do that, I mean, part of the story is also in developing new probes, okay? Part of the story is in developing new probes. So I will tell you about some new probes that we are proposing in this regard. So let me start with the simple thing, which is prehistory, okay? This is prehistory. So the simple thing is that, you know, fermion pairing from repulsion has already been recognized long time ago. I mean, this is not a new subject, okay? Since '65, Kohn and Lattinger essentially propose some sort of, pairing mechanism, okay, due essentially to Friedel oscillations in weakly repulsive systems, okay? In weakly repulsive systems. And indeed, the characteristic of this type of pairing is that it involves large orbital angular momentum, okay? So some years ago, indeed, with Leonid Isaev, that student, we basically proposed some sort of different mechanism. It's not BCS. It's basically based on local kinetic energy frustration, okay, where essentially you can have some, local energy fluctuations because of inhomogeneities. Okay, so you don't have some sort of standard lattice, but you have some sort of inhomogeneities, and then what happens is that you can induce some sort of pairing and then superfluidity or superconductivity in a strongly repulsive system. So indeed, the superfluidity happens because it's strongly correlated. It's not because it's weakly correlated. And indeed, we could achieve pairing with a small orbital angular momentum. Okay? So what we are trying to do here is trying to extend some sort of these ideas now in the context of optical lattices. Of course, we will have to change a few things because, as I mentioned before, what we want is to use the experimental capabilities. So let me, I mean, this is part of the story. It's also similar to Saro's talk, that where the main ingredients are essentially these clock state atomic systems that are, I'm not sure, I'm afraid to touch because the thing is that it's moving, it's not moving. So let me use this. Okay, doesn't work. But OK, so the main ingredients are essentially, we have some alkaline earth atoms, OK, where we are using the states, the multiplets 1s0 and 3p0 that have total angular momentum 0, OK, and they are separated by something like 10 to the 14 hertz, OK, and indeed the whole idea is essentially trying to induce some sort of spin orbit coupling in the system, okay, and indeed engineer some subsystem that acts as a mediator. Okay, this works better. As a mediator, okay, in order to essentially generate a pairing and superfluidity. So what we want to do now is play with these two states, where we are going to put the atoms either in this state 1s0 that I call G, or 3p0 I call E, and essentially generate some sort of superfluid. Okay, that is idea. Now, in principle, there are many nuclear states that you have in these atoms, and the thing is that because the nuclear spin is 9½ so in principle you want to resolve with a magnetic field any of these states. You can choose any of these states. So you apply a magnetic field, and basically you choose one of these nuclear spins, projections, okay? And in principle, these atoms have an S-wave scattering, and basically by applying this magnetic field, and essentially selecting one of these nuclear spins, what I want to consider are the polarized case, and in that way, the symmetric part, okay, the symmetric part disappears. So the only thing that I'm dealing with is the antisymmetric part, okay, of the interaction. So now, let me tell you what is the Hamiltonian that essentially experimentalists can handle. So the idea is, I drew here essentially two lattices. So there is one lattice that is this blue lattice that have the G atoms, okay? These are going to be the delocalized or mobile atoms, fermions. And then I have these localized ones, okay, that basically, when I form these two lattices, these localized ones can only move here, okay, in between this dimer. So this height is so large that they cannot tunnel, okay? They will be most of the time here, okay? And the ones that I'm interested in are essentially the G ones, that are the ones that are going to delocalize, and hopefully these are the ones that are going to form a superfluid, okay? So the Hamiltonian that characterizes these different interactions I was talking about is essentially Hamiltonian that involves a kinetic energy of these E atoms here that is basically moving mostly on this dimer place. Then there is some interaction between these G atoms. I mean, this is of the density type. Okay, then there is, kinetic energy, and there is interaction energy between the G and A atoms, and there is also exchange. So in principle, you have all this, and essentially I characterizes the dimer side. This is I plus 1, and essentially N characterizes this nuclear spin. But if I polarize, essentially all this exchange and interaction between the G becomes essentially density-density interaction between the polarized nuclear spin species. Okay? So the idea is that basically now I have, and I'm showing this first in one dimension. Okay? The same idea is generalizable in 2 dimensions, as I will show you later, or 3 dimensions. So let me now tell you how is that pairing emerges. I mean, it's a very simple idea. The idea is that I look at essentially, let's assume I concentrate in one a couple of sites, okay, these dimer sites, where I will have essentially one E atom, one of these E atoms in these wells, okay, and now I can put either 0 G atoms, 1 or 2, okay. So now the idea is that I will try to look at under which conditions I may get an effective interaction between the G atoms that is attractive, okay? So if I am, solving this problem, it's a very simple problem. I mean, quantum mechanical problem where you have the subspace where there is one E atom, and then, the subspace with 0, 1, and 2 G atoms. It turns out that if you choose the symmetric state, this will be the G atoms effectively will repel. Okay, so that's not the situation where you want to work and operate in this optical lattice. The situation that you would like to be in is essentially the one where you are in the antisymmetric state, okay, the antisymmetric state of the E atoms, where essentially you prefer to have pairing. Okay, so that's the idea. So the pairing, if you want, this is some measure of pairing. The pairing is proportional to minus V squared over 4G. Actually, remember, V is the interaction between the E and G atoms, okay? And JE is the kinetic energy of the E atoms. Now, this is just for a couple of sites. Now, if you want to solve the many-body problem, indeed, the same thing I mentioned before is equivalent to do a Schrieffer-Wolff transformation, okay? And if you do a Schrieffer-Wolff transformation, essentially what you get as an effective Hamiltonian for the G atoms is basically an off-diagonal kinetic type of energy, okay? And then you get an attractive interaction between the G atoms, okay? So there was, remember, I started with 2 bands, okay? I basically produced some sort of inhomogeneity in the E band. This inhomogeneity in the E band produces some local fluctuation. These local fluctuations effectively produce pairing, okay, in the G atoms. And indeed, that's not enough. I mean, the other thing I mentioned I need is some sort of a spin-orbit coupling. And indeed, the spin-orbit coupling comes effectively, okay, through this type of kinetic energy that comes just because of the doubling of the unit cell. So you see, I'm playing here the role, the same kind of thing that you do with SSH, okay? So by distorting the lattice locally, I am producing effectively on the other particles an spin-orbit coupling, and at the same time, by adjusting the state, I can get attraction. So in the end, I am getting a Hamiltonian that is number conserving, is attractive, and it has a high probability to be topological, okay? So that is the idea. So indeed, you can, in order to see what, there are many different things you can do. I don't know how to solve exactly this problem. I have no clue. Of course, you can put in the computer, no problem. But let's try to do the simplest thing one can do, okay? Well, first, what we can do is we can rewrite this Hamiltonian in the basis that is a basis that diagonalizes essentially the spin orbit part of the kinetic energy. This is the F. And then let's see what kind of Hamiltonian you get in that case. So if you do that, indeed, the kind of Hamiltonian you get is a pairing Hamiltonian. Okay? So indeed, I mean, it's easy to realize that, I mean, just without doing any calculation, that this Hamiltonian I gave you before, it will be a type of p-wave pairing Hamiltonian. And that's a very good candidate for a topological superfluid. Okay? So indeed, you can do more. I mean, the more things you can do, indeed, you can do some sort of unconstrained mean fields just to see the stability. You know, either you put, as I said, in the computer and you solve everything, or you do the best you can do with a trivial mean field, but unconstrained because I want to see the stability of the phases. I want to see if these phases, you know, is very unstable or not. And indeed, it is not. We are allowing all kind of, you know, bad things like magnetic, you know, charge density wave, loft, all kind of things. And indeed, you can see that even if you are doing, you know, if you construct the phase diagram for this quasi-1D model, this phase diagram will contain a topological superfluid phase that is pretty robust. Okay? Indeed, the trivial phases appear. So if you solve the problem without constraint, it turns out that there is a trivial topological phase. Okay? It's not just the topological, you know, the topological one, superfluid, but there is a non-topological one. But as soon as you put the unconstrained, you know, the charge density wave picks in here, but it's still, the topological phase is pretty robust. So that is, you know, it's a very good indication that we can use in principle these ideas to realize these superfluids, which, you know, can be realized basically with what we have right now. Okay, without heating, without losses. We are not using phase-back resonances. That's the thing is important. Okay, it's extremely hard. You talk to an experimentalist, it's very hard to get, you know, p-wave phase-back resonances. We are not using. So the way we are getting this type of p-wave superconductors, or superfluids in this case, is by playing with effective interactions, by using some sort of medium, okay, effective medium that induces this physics effectively. Okay, it's a trick. So, but the same trick you can play in 2 dimensions or in 3 dimensions. Okay, here I'm showing you a trick in 2 dimensions, which is pretty similar to the original work that we did with the onion. That is, you know, for example, you can put this type of Pyre style of distortions, or, you know, this in plaquettes, okay, like here, okay, and the Hamiltonian is essentially exactly the same Hamiltonian I had before. It's just that now, you know, the geometry and the topology of the thing changes, but it's exactly the same thing. So by inducing this type of inhomogeneities, I can now generate, indeed, I can now generate using exactly the same ideas. You know, here I'm telling you for the case, before I work with just a pair of sides, and I show you that you can get effective, you know, pairing. Well, you do the same thing now with 4 sides. Okay, and you realize by looking at the states of the 4 sides, you realize that if you work in a particular state, indeed, you can induce attraction. Okay, again, another way of saying the same thing that I am saying here is if you take the many-body system and you induce, you know, through a Schrieffer-Wolff transformation, you transform your problem, you will get this type of interaction. So that's the effective attractive interaction that you are getting when you make this type of distortion. You could make other types of distortion. That's not the only one that you can make. But the idea is that in principle, this is doable. Okay, and now, you know, again, we can ask the question, okay, what type of superfluidity or superconductivity we have in this system? Okay, I mean, again, I do the same trick. And the same trick is I go, again, to the basis that diagonalizes the kinetic energy, that the kinetic energy is some sort of a spin-orbit coupled system, okay? And what happens is I get this type of Hamiltonian here, and this type of Hamiltonian has 2 competing phases, okay? It has a px wave and has a p plus ip wave phase. So through this type of system, now you are realizing a p plus ip superconductor, a superfluid, okay? These are charge neutral systems, okay? So a P plus IP superfluid, okay? Okay. And of course, I mean, all these ideas are necessary, okay? All these ideas are necessary because, as I said, we want to realize physical systems that are topological superfluids and where I can address the issue of Majorana in number-conserved systems, because these are number-conserved. You know, the number of atoms is fixed inside your system, okay? So now let me tell you a set of new probes that we are proposing right now, essentially to address this. By the way, experimentalists are starting to do these systems in Gila, okay? So let me tell you what is the type of new probes that we are proposing. I mean, with the goal, of course, of probing topological superfluidity, but in principle, even to probe superfluidity in situ, okay? No superfluidity by time of flight or anything like that, but in situ, okay? So the third thing I want to tell you is there is a new effect, okay, that you can get, okay? Indeed, it's a new effect. It's a kind of synthetic magnetoelectric effect. So it's synthetic because, of course, there is no charge here or anything like that, okay? There is no real, you know, magnetic field, okay? But you can imagine that you apply a magnetic field like this, okay, in your optical lattice. I mean, this can be done, you know, with lasers. There is no problem to do that. And indeed, what happens when you apply this kind of thing, it happens something that is like the reverse of the Edelstein effect. Okay, so you apply a magnetic field and there is a supercurrent. That is the idea, okay? So the idea is that we are going to apply this magnetic field. For example, this is in the one-dimensional case, and then what we are going to generate essentially is a supercurrent. So let me show you. Let me show you how this. So how much? 5 minutes. So let me tell you how you calculate the supercurrent. Indeed, I mean, this is the usual way. I mean, I'm just showing you here. I mean, the simplest case, how is that you calculate, you know, the current in a simple lattice systems, which is non-interacting fermions, where you do the usual Bayer substitution and you calculate the derivative of the Hamiltonian with respect to this flux. Of course, I mean, this current is going to be 0 there. Okay, now for our case, if we do a similar type of procedure, okay, but now for our Hamiltonian and, you know, sorry, for our problem, I mean, with the dimerized unit cell, as we have, it turns out that this supercurrent is given by this expression here, okay? And you see that, indeed, the supercurrent appears because of the application of this magnetic field. In this case, I mean, the magnetic field is applied along the y direction, okay? So there is some sort of diamagnetic part that appears in the response, I mean, in the supercurrent. And indeed, you can compute that. You can take now, you know, these mean field solutions, whatever, and you can compute. And indeed, what you see is that in this phase diagram we had before, in the topological superfluid part, there is indeed a value of supercurrent. Okay, this is the blue, is this line here. Okay, there is a supercurrent different from 0 and then goes to 0 in the charge density wave part. Or, you know, this star is this point going through to the band insulator phase, basically doing exactly the same thing, but of course it goes to 0 at a larger value of mu. Okay, so this supercurrent is going to be a fingerprint of this superfluid, of this topological superfluid you have there. Okay, by the way, I mean, we check that if you take the IC model, not the IC model, the key-type model wire, and you do the same calculation, you have the same effect. Okay, so trivially it's the same effect. It's not something particular to this problem. Okay, of course, what one can do also, I mean, after applying this magnetic field, is to do also time of flight measurements. Okay, look at the momentum distribution asymmetry as a function of Vy. Okay, and indeed that's another signature. Okay, of this superfluidity. Okay, because there is an anisotropy here. I'm plotting the anisotropy here. Is nu sub p. Okay, so I mean this is also a fingerprint of the superfluid. Okay, so let me try to summarize what I've been trying to tell you in a sort of chaotic way. I mean, as I said, this was an experiment using this tablet that didn't go so well. But let me tell you what is the idea. The idea is I want to really test whether I can manipulate, okay, and I can generate this non-abelian braiding, okay, with these Majorana modes, okay? So I want to generate this Ivanov game. And the thing is, I want to generate in a number-conserving system. So that is the same motivation, in principle, that Saro had in his talk, okay, yesterday. It's exactly the same motivation. His route, his path is different. His path is he's trying to induce spin-orbit coupling, okay? He's using other type of interactions than the one I'm using. The one I'm using are, in principle, the ones that the experimentalist tells me we can do now, okay? These are the things we can do now. That is, okay, so you can make all kinds of optical lattices, okay? So why not just superpose two optical lattices? They can do that. So I can have now two types of lattices, one that is essentially introducing some sort of distortion, okay? Here I'm showing you a one-dimensional case, some sort of distortion, and the other is the atoms I'm interested in, I want to test, okay, are mobile, okay? And through this game, that is using an intermediate system that induces, even though the interactions are repulsive, induces an attraction in the mobile system. And moreover, because of the particular way I introduce distortion, there is an effective spin-orbit coupling, I can get a topological superfluid. Okay, that's the trick. Now, and what I told you, I mean, basically through this talk, is that, you know, this is some sort of mechanism, new mechanism for repulsive fermionic superfluidity. I told you how to generate topological P-wave superfluidity. And I also told you about this kind of anti-Edelstein effect, where you take these systems, you apply a magnetic field in your system, and you generate a supercurrent, okay? So in that way, we will be able to detect that superfluid in the optical lattice. Of course, there are many, you know, many open questions. Well, this is basically saying that, you know, the idea is to use realistic experimentally controlled interactions. I mean, we want to avoid heating, okay? And also, we want to avoid losses. That is the problem with the P-wave phase-back resonances. Of course, there are all kinds of open questions. Still, and I'm working with Manik Neil on the thing. Basically, I'm working in trying to detect and manipulate Majorana modes within these type of things, okay? So there are some platforms that have been proposed by people from Microsoft, basically with wires, okay? With K-type wires, okay? There are some platforms basically measuring, you know, fermion parity, okay? We are doing something slightly different, but you know, we are essentially very interested in seeing if we can do that in a number-conserving system. And I think that, you know, from my perspective, I mean, to me, still, this Majorana thing is a mystery that must be solved. Because, as I said, just, you know, claiming that you have a Majorana because you have a zero-bias conductance peak that you have for many other reasons, or you have a localized thing at the end of a wire, that is useless. I mean, you can say it's a Majorana, fine. If you're happy, it's fine with me. But the thing is, that's not the reason why you want to introduce this concept. The reason is because you want to do something useful with that thing. And the useful thing is the non-abelian braiding. That is the useful thing, okay, to do topological quantum computation. Okay. That's it.
Which you have got in your calculation, I think you do the in-field type approximation, Hartree-Fock type of approximation after this. Okay. And so the general conjecture which you are doing at the very end of your seminar, how far it will be reliable? How far it will be reliable, because the basic source is the Hartree-Fock approximation, how the topology will is that?
Okay. I didn't mention something before. You know, the previous work I did, basically, I tried to answer some of the questions I mentioned before. I tried to answer by inventing a new model, Okay, so I invented a new model that is Bethe-Ansatz solvable, okay, that we call a Richardson-Godin-Kitaev model, okay? And that exactly solvable model is exactly solvable, okay? And there I could do many things, and I know it works, okay? I know it works because I have the exact solution, and I know it works. Now here the motivation was slightly different. The motivation is I want to realize now, I mean, the Richardson-Godin-Kitaev model is a toy model. It's not the realistic model. You don't have non-local interactions, okay? But it's very useful because you get a lot of insight by solving this problem exactly. Okay, in particular, how is that you can generate these Majorana many-body modes, okay? Now, here the motivation is different. I mean, I'm not saying that this phase diagram there is, you know, the ultimate truth. What I'm saying is that based on that experience, I know this model will have, okay, a topological phase. I know that based on the other thing I did, okay? So if I do the mean field, I see that also is there. And if I do the worst mean field, because when you are adding this Hartree-Fock, I mean, the Hartree-Fock and other things is basically always want to get inhomogeneous phases. That's the point. I mean, always this type of mean field. I mean, by the way, we are doing in large cells and things like that. All these mean fields always favor inhomogeneous phases. So it's bad for homogeneous phases, okay? That's the reason why we did it. And still you have this topological phase, okay? So if you want to solve the problem exactly, it's very welcome. I'm not sure there is an exact solution for that, but.
So my question is, what is the TC of this phase? I mean, as I understand it, in the S-wave case, you use the Feshbach resonance, and so you get TC comparable to the Fermi temperature. But intuitively, in this case, aren't you going to get TC very much less than TF? And if that's the case, will you practically be able to cool the fermionic system into this new topological phase?
The answer is yes. Yes, I mean, that's the claim is yes. I mean, indeed, that's what Ana Maria has been talking to the experimentalists in Chile. They can cool. I mean, basically, yeah, I mean, it's a good question. I mean, basically, it's going to be related to this, you know, hopping amplitude that we have in the lattice. But when you put the numbers, it turns out they can do it, they can cool it. But that's a very good question. Because, of course, if you cannot cool that thing to the superfluid phase, you're not going to see. Absolutely, correct.
So what's the reason for you to avoid FFLO states? Because you were saying
because I'm not interested in the FFLO. I mean, I'm not trying to avoid them. I am not interested. I mean, if you are interested, maybe that's something that you can even see if this is, you know, if you are in a regime in the optical lattice where you see those things. But that's not my interest right now. Okay. My interest right now, let me tell you what my interest is again. My interest is in trying to see whether I can manipulate and do non-abelian braiding with Majoranas in topological superfluid, which is not necessarily the same thing as manipulating Majoranas maybe in quantum Hall systems. It's not the same, okay? So my goal, my interest is there. But if someone has interest on these other parts, I mean, it's fine, but it's not my interest.
In your Hamiltonian describing the two species of atom, only one set of atoms has an on-site interaction. Why?
Only one? No, in principle, the interaction, I mean, both have. Both have.
But the quartic one appeared only at one. This is the first Hamiltonian you showed.
Okay, let me, I don't know how to, you know. This is...
These two colors, colors.
Yeah, there were many things, two colors here. But many, I mean, and these are the colors of my team, soccer team. Let me tell you. Sorry. This Hamiltonian?
Yeah, I think so, yeah.
Yeah, in principle, this Hamiltonian, you see...
The UGG, you have
yeah,
quartic.
Exactly, exactly. But you see, when you have the polarized one, this goes to zero.
So this is helpful to trace one sort of...
Exactly.
That is the reason. Okay.
Exactly. Exactly.
Okay.